of the system. Okay, I'm just gonna do a very quick review of a concept that you've seen before, but I'm not sure how fresh your memory is, so I'm just gonna do a very quick review. This concept, it's called body plot. So many times you might not actually have the transfer function. So we don't know what the transfer function is. But we might have the like the body plot. We might have basically, we know how our transfer function changes versus frequency, but we can't write it down in closed form. Okay, so this transfer function has a magnitude and has a phase. Okay, before we go further, so like I'm just gonna show this the magnitude of transfer function with this symbol and the phase of it with this symbol. And we show the magnitude in terms of something called dB, which is basically 20 log of mg in base 10. Okay, in some textbooks or for some other concepts or some other subjects, you might have a different definition here. Sometimes like it's 10, sometimes like they use like 10 log or like another coefficient here, but like here, like we're just using dB, which is 20 log of our magnitude. So some concepts that we should know, and I'm gonna explain later why these concepts are important. So let's assume that we have a transfer function that has this body plot. The body plot basically shows the magnitude and phase of the transfer function with respect to the frequency. And we show our frequency axis is logarithmic in the scale. So it's like, let's say if this is 0.01, this is 0.1, this is 1, this is 10, this is 100, and so on. Okay, sometimes you might want to show 0.001, and like it goes like that. Same thing here. Okay, so let's just assume that we have a system that has this kind of, just like say 40, 20. This is an example I got from Dr. Kim. So minus 20, minus 40. So let's say that like we have transfer function that its magnitude has this body plot. It goes up to here, and then with the slope of minus 20 dB goes to here, with the slope of minus 40 dB goes up to here, and then with the slope of minus 20 dB goes to here, and then stays here. Oops. So this is what's happening here. This is minus 20 dB per decade. Each of these is 1 decade. This is minus 40 dB per decade. And this is minus 20 dB per decade. And this is mg in terms of decibel. And we also have to do the phase. Let's say our system starts from 0 degrees and let's say at let's at this point. Oops. Okay, so in 2 decades it gets to negative 90, so this is minus 45 degrees per decade. Minus 45 degrees per decade. 0.11, okay. And in again in another minus 45 gets to 180 degrees. Negative 180 degrees. Okay, so this is also the same. Let's just this is like an example. So let's assume that we have this. I just want to show you some concepts. The frequency at which the magnitude becomes 0, so in this case it's somewhere around here, it's called crossover frequency. So crossover frequency is the frequency at which magnitude of g of j omega c becomes equal to 0, right? So this, you can see that here in dB, right? So if this becomes 0, it means that magnitude of mg is equal to actually 1. It's called the unity. So it means that in 0 dB, so it also means that it's equal to 1, right? So mg is equal to 1, not in dB, right? If it's not in dB, it's equal to 1, right? Because log of 1 becomes 0, right? So this is called crossover frequency. That's one concept that you should know. We have, so this is the first thing I wanted to mention. The second concept, it's called phase margin. So you're gonna find out like why these are important later, but the phase margin is basically at the crossover frequency, we look at the phase and we see how far it is from the negative 180 degrees. So this is gonna be the phase margin. Okay. Just remember these concepts. Later on, you find